So when you're using this expression for impulse, um, obviously this means get the area under the curve on an FT graph. So if you've got a force time graph whose area is easy to find, the integral is no more than just doing basic geometry. So in the case of this triangular area, the impulse is just 1/2 base times height. You then set that impulse equal to the change in momentum, and you can relate the effects of force over time to motion. If you have a more complex curve, but it still could easily be broken into simple geometric shapes, you use basically the same strategy. So this curve is complicated, but it was easily broken into easy to deal with pieces. So I just found areas of triangles and rectangles, added them all up, and then once again set that impulse equal to the change in momentum. The trick becomes when the curve gets easily described using a mathematical function, but not simple geometric shapes. Let's take a look at that. So in this situation, we want the area under the curve on a force versus time graph that's best described using this function. But interestingly enough, we only want a piece of the area under that function. If we zoom in, we only want the area bounded by the function, the t-axis, and then vertical lines at 0.37 and 0.91. How can we do that? The easiest way I know of to think of this is that we could find two areas. So if we zoom in, if we find the area between 0 and 0.91, that includes this purple area that we don't want. So mathematically, an easy way to get the area we do want is to find the entire pink area from 0 to 0.91, then find the purple area from 0 to 0.37, and subtract the two. And that gives us the area we want. The best way to do this is something called a definite integral, and I want to use this problem as an example on how to do one. So the first thing we do is we write the impulse equation like we were doing before, but we add something to it. We put these things called limits at the top and bottom of the integration symbol. And you'll notice that they are the left and right boundaries of the area that we want. It's a pretty straightforward integral at first, like we've done for indefinite integrals. We plug in the force, and we take the antiderivative. So we end up with 17 over 4t to the fourth. Notice though, instead of putting plus c, I've put this bar here, and I've left the limits in place. So all you do to finish your definite integral is you plug in the upper limit as t, and that will get you the pink area. And then you subtract the same expression with the lower limit plugged in, that'll get you the purple area. And the difference between the two is the area that you're actually looking for. So the impulse in this problem ended up being 2.833. Not just like in the other problems, we take that impulse and set it equal to the change in momentum to get our final answer. So hopefully that helps you with the process of a definite integral. It's going to be really helpful for finding areas under the curve in impulses, therefore.